All right, so today we'll learn geothermal energy. Okay, another way to produce electricity. Okay, and again, here's one way to produce electricity. We keep seeing this. Okay, so what is this? This is a magnet. This is one pole of the magnet. This is the other pole of the magnet. This is the magnetic field. So this is the north pole. The blue lines are magnetic fields. So in this magnetic field, all you do is if you take a piece of wire and if you turn this wire, what you get is an electric current. You see this electric current is driving this needle. Okay? So again, like we keep saying, there's no free lunches in the world. It seems like you're getting electrical energy out of it. Well, what you did was you did work to turn this wire. And to do work, you need energy. Anyway, so if you put in $100 worth of energy, you get $100 worth of electricity out. Now, we've learned various technologies for turning this wire. In a windmill, the wind turns the blades, which turns this wire. Your ultimate goal is to turn this wire. In a dam, the flowing water turns this wire. How do you turn this wire in a nuclear power plant? I'm sorry?
Boil water.
You use split nuclei, which produces heat. You use that heat to produce boiled water, and the steam that produced turns this wire. The steam turns a turbine, which turns this wire. You guys understand all of that? Okay. Ultimately, your goal is to turn that wire. Okay. You burn coal, you boil water, the steam turns a turbine, which turns this wire. Okay? Today, we're going to learn a way to turn this wire. Okay? Again, we always start off with heat. Okay. My rough. All right, so today, this is ground. Okay. It turns out that there is heat coming in from underneath your feet. What do you do with heat? You boil water. What do you do after you boil water? The steam is going to turn a turbine, which is going to turn that wire. Okay? Now, here's the deal. Okay. There is a solar energy coming from the top. You know how to harness that. How do you harness that? You've used solar panels to harness that. Okay. Now we're going to look at this guy. Now, if the amount of solar energy coming from the sky is 2,000 times more than the heat coming from the bottom, you can harness this with an efficiency of 20%. You can harness this with an efficiency of 20%.
At the same time or separately?
No, what I'm saying is, if you concentrate on doing this business, picking up solar energy, you can harness it 20%. What does that mean? Your solar panels are 20% efficient. Of the $100 worth of sunlight falling on your solar panel, you're producing $20 worth of electricity. Out of $100 of heat rising, you're harnessing $20 of electricity. But there's 2,000 times more money falling from the sky. Why do you bother with this thing? That's the question. Did you guys understand that? Okay. So this guy is not going to solve your world problems. What is this guy? If you're walking on the sidewalk and you see $5, are you going to pick it up? Yes, you are. I am going to pick it up. Okay? All right, that's what this is. So geothermal energy is a niche solution. Okay? It's not going to solve the world problems. In certain locations, there's more heat coming up, and so you'll harness that. Okay? So for instance, Iceland gets more than half of its energy via geothermal energy. Okay? I'm just giving you the big picture first. Okay? Do you guys understand that? Okay. All right, so let's see how much geothermal energy we harness. Okay. So we'll look at the big picture first. Okay. In the world today meaning in, well, whatever, by the 2020, there's 16 gigawatts. Where's mine?
I know, I'm sorry.
You perpetually sorry.
I am. Oh, I'm so long.
All right. So there's 16 gigawatts of electricity harnessed via geothermal energy. How much do you need to run the world? Here it is, 16,000 Hoover dams. That's 16 Hoover dams worth of energy that you harnessing worldwide in geothermal energy. That's 0.1%. Okay, so it's like for every dollar you're bringing home, or for every $10 you're bringing home, 1 cent is being contributed by geothermal energy. Okay. All right. So it's a very niche solution. Okay. Did you guys understand that? Yeah. Any questions on that before we go on to the slides?
So with the $5 analogy, you were just saying like it's $5 versus $500, but you still want to put the $5 in your pocket.
Yeah,
You
yeah.
want to use that energy.
Yeah, I'm going to use that to buy coffee that people didn't bring me. I mean, I'm not going to pay my mortgage. I'm not going to pay my mortgage with that $5. That's the point. Okay. You can't depend on students no more. She wasn't even listening. Okay. All right. So here's the deal. So we'll put numbers behind that. Okay. Okay. As you go down. As you go down deeper, the temperature rises, and that's what's indicated by this color diagram. Okay, so the deeper you go, the hotter it gets. Now, if you want to boil water, you want to be somewhere where it's about 200 degrees Celsius. Okay, and to do that, you have to go about 3 to 4 miles deep. Okay, so the idea would be the following: if you wanted to produce electricity, just dig a deep hole. Pour cold water in there. That water will get hot. At 200 degrees Celsius, it'll boil. And then you can get steam up, and you can use the steam to turn that turbine to produce electricity. Yeah. So if you want to produce electricity, that's how far deep you have to go. But this is a very good solution. Okay, and we can use this. So up north and stuff like that, for heating and cooling, you can use geothermal energy. Okay? And that's a very good solution. Okay? So for that, you just have to go about 50 to 100 feet. Okay? What you do is, at 50 to 100 feet, and I'll show you a diagram, the temperature is constant. So what you can do is, for during the winter, when you want to warm your house, you send down air, or, well, there are other ways of doing it. Okay, you can think of sending down a fluid. It warms to that temperature, that steady temperature. Okay. So in Florida, if you're down here, if in Florida the steady temperature is, take a guess, what is the steady temperature in Florida? 72, close. And here's how you remember it. That's the temperature of the springs. Okay. So in the winter, what you can do is 72 is a plenty warm temperature. You can send the cold air down there. It'll warm up to 72 and bring it back to your house. Okay. So no, that was in the summer. Send warm air and then bring it back up. In the winter, I'm just simplifying this. You can take the cold air in your house, send it down there. It'll warm up to 72 and come back up. Did you guys understand that? Okay. Now there are better, more efficient ways of doing it, but that's the idea. Okay. So you have a constant, steady temperature at this level, and you can use it for heating and cooling. Okay. All right. So you want to produce electricity, you got to go 3 miles deep, 4 miles deep. You want to just heat and cool, you just go about 100 feet deep or less. Okay. And this can be significant up north. Heating and cooling bills, heating mostly bills are about $5,000 a year. Okay? And you can cut it down by half, so half to a little more. So you can cut down your heating and cooling bills to $2,000 a year. Okay? So if you put in those systems, okay. All right, so we've already said this. Geothermal energy can be only a niche solution. We're just picking up money on the sidewalk, okay? You're not paying your mortgage using that money, okay? So again, according to these guys, I keep throwing this graph at you, but these guys, so I mean, they're fairly smart guys, and if they're wrong, they won't be wrong by too much. Okay, so by 2050, 40% of the global energy will be coming from wind, solar, hydropower will be a very small portion, and geothermal energy will be less than 1% of the world's energy. Okay? So we are talking about a small contribution. Geothermal energy rising from under your feet is about 2,000. The solar energy falling on you from above. Okay? So if you want to become a billionaire, solar energy is what you want to pursue, not geothermal energy. Okay? All right. So now we're going to answer this question. So heat is rising up from the bottom, from the ground. Where is this heat coming from?
Core.
I'm sorry?
The core.
Okay. Will you run out of this heat?
One day.
I'm sorry?
One day.
One day. Okay, so, I mean, probably you won't have to worry for another 5 billion years or so. Okay? So, but let's see where is this heat coming from. Okay, so let me illustrate that. I'm recording this. They won't be able to see this, but okay, let's do this. So I'll drop this keychain. What happened? The keychain fell, but so let's talk about energy is what we're talking about. I drop this keychain. This has potential energy that got converted to kinetic energy, energy of motion. And now what happened to that energy?
Potential.
I'm sorry?
Potential.
It got converted to mostly heat. Okay? So, when the earth was forming, okay, so when the earth was forming, so it formed from there, stuff falling in, all this stuff. Okay, so the same thing happened. Okay, so all that heat from the potential energy was trapped up, is down there, and that is rising. Okay, did you guys understand that? Okay, so this is, when did the earth form? When did the earth form?
A long time ago.
I know. Let's put numbers to it. 4.5 billion years ago. 4.55 billion years ago. Very good, my friend. Okay? So that heat is still rising. Okay? All right, that's 25%. So, again, yes?
My stomach is growling.
How about that?
My stomach's growling.
Oh, I see. Hungry. She didn't bring you a sandwich,
I
huh?
did.
All right. You can eat it.
I told her. She won't.
She
She's got
won't.
Anxiety.
Huh?
She's got anxiety.
Oh, I see. Oh, I see. Competing forces here. All right. So that's 25%. The other 75% is, so these guys are radioactively decaying and producing the heat. Uranium, thorium, and potassium. And so these guys have a half-life. This guy has a half-life of roughly 1.25 billion years. And hi, Erica. Can you remind me of what's half-life? You guys remember? All right. So if I have 1,000 atoms of potassium, the half-life is 1.25 billion years. In 1.25 billion years, 500 of them would have decayed and half of them are left behind. Okay? So what I'm saying is, so 75% of the heat is produced by these nuclei decaying, and these guys will be decaying for a long time. They won't be gone for a long time. Okay? So they'll be producing heat for a long time. Okay? All right, so that's where the heat is coming from. Okay? So 25% is primordial heat and 75% is from radioactive decay. Okay? What we are trying to say is if you are even going to pursue this source, is this source going to be around? Okay? And again, we're going to pursue this source. Where are we going to pursue this source? Only where it's easily available, cheaply available. Again, we're just picking up money from the sidewalk. Going back to my analogy. Okay. All right. So this picture tells you a lot. This is how many, so it's 16,000 Hoover dams is what's needed to run the world. 16,000 Hoover dams running 24/7. You see there's plenty of sunlight falling. Okay? You just have to harness that. Okay? There's plenty of wind. So, and that's what the world is doing. The world is not stupid. That's what they're pursuing, wind and solar. Okay? And even though they're the cheapest sources, why aren't we using them right now?
Because we don't have cheap enough batteries.
It's cheap enough batteries, okay? That's what's preventing us, okay? So here is coal, okay? So I'll just tell you what this number means. Again, this is a very good diagram to remember. This is terawatt hours, terawatt year. What that number means is, okay, let's say this is 15. 90 by 15 is 60. So if you ran the world entirely on coal, you can run the world, you can run it for 60 years. That's how much coal we have. That's what that number means. Okay? So you can calculate that. These are all finite resources. Uranium as well, but there's other ways of getting around it. Oil is a finite resource, natural gas is a finite resource. And these numbers will tell you how many years you could run the world entirely on those sources. Okay. But anyway, we are talking about geothermal. So you see again, geothermal won't pay the mortgage. Okay, so average geothermal heat flow from the interior of the surface is 87 milliwatts per meter square. What this means is here's a meter square. Here's a meter square, and the amount of heat rising for every meter square is 87 milliwatts. Okay, how much solar energy is falling? 170 watts. For every meter square on Earth, 170 watts is falling, and 90 milliwatts is rising up. Okay, so again, like I said, 2,000 times less. Okay? So solar energy can solve world energy problems, while geothermal energy can only be a niche solution. Yep. I keep repeating myself, but I just want to emphasize that. But if you live in Iceland, then geothermal energy is your friend. Okay? So here in the U.S., where do we want to harness? So you see, in these areas, the amount of energy, geothermal energy rising up is twice the global average. Okay? So again, if you are going to have a geothermal plant, you're not going to build it anywhere around here. Okay? What you learn shortly is the best sources are near plate boundaries. Okay? So wherever you have plate boundaries around the world, that's where you have geothermal plants. Okay? So heat flow can be as high as 150 milliwatt per meter square, twice the global average. Okay, so Iceland straddles the mid-Atlantic ridge. There is the mid-Atlantic ridge, and And Iceland is, I guess, somewhere there. Okay. And because it straddles the mid-Atlantic ridge, the crust is very thin here and a lot more heat rises up. Okay. And so Iceland gets more than half its energy from geothermal sources. So geothermal heat flow is the greatest near plate boundaries, and so that's where you harness them. Okay, so here are the plate boundaries, and these yellow dots are the geothermal plants. Okay, so U.S. harnesses the most geothermal energy in the world. Yeah. We harness the most, and again, all of them where the plants are there next to plate boundaries. Yeah.
What's a plate boundary?
What is the plate boundary? Okay. So this is the Earth. Do you know the radius of the Earth? Okay. Does anybody know the radius of the Earth? You're looking at me like, why should you know it, huh? What's that?
I said just off the dome.
Yeah, off the dome.
Do you know the radius of the Earth?
I just
Yes,
wrote it
you
down.
wrote it, so
I can tell you that in my sleep. And she didn't even bring me a donut for that. I'll never forgive her. All right, so this is the plate boundary. This 40 miles, this is about 40 miles, okay? I'm giving you rough numbers. So 40 miles, that's 1%. So think of an apple and its skin. Yeah? Okay, this thing is broken up into plates. Okay, so this is rigid, and this is called a lithosphere. It's broken up into plates, and that's what you saw. Those are the plates. So that's one piece, and that's another piece. About 80 big pieces. I guess we'll have to look up the numbers. Okay. All right, let's say 80 plates. Okay. Yep. Go ahead.
does the geothermal, so in Iceland you said that they use that, they harness that. Is that why they have those like springs and stuff? Do you know what I'm talking about?
Yeah, we'll.
The hot springs, and there's always like
Oh,
steam
yeah.
and
Yeah, the Blue
stuff.
Lagoon and all that.
Yeah.
Yep. That's it.
Okay.
So, all right, so going back to the plates. Okay, so these plates are these are rigid plates that are broken up, and this is they're about 40 miles thick. Okay, and what's happening is, so as you go deeper, all the weight of this thing increases the pressure, and so underneath, just below the plates, there's a layer of rock that has become plastic. So this has become plastic. Asthenosphere. And so think of these plates as wooden plates, pieces of wood, and think of that as honey. So here are these plates, wooden pieces, floating on honey. Okay. All right, now imagine the following. I'm, again, just making up, trying to give you some analogies. Let's say you put this whole thing on a stove and heat it. What will happen? The honey gets heat, and it'll have, I'm sorry?
Bubbles.
Bubbles, convections. Okay, so here's honey. As the honey bubbles, it'll push on the plate like that. And these plates are constantly moving. Okay, the plates are moving about 2 inches per year. They're constantly in motion because of this heat rising from the earth. Okay, So this plate is moving in that direction, that plate is moving in this direction. Let's say this plate is moving in this direction, this plate is moving in this direction. Is the surface area of the earth increasing? No. Okay, so these plates move apart because magma is rising and new plate is being created. But we just said that the surface area of the earth is not increasing. So what is happening here? This one plate goes underneath another plate and gets an equal amount gets destroyed. Okay?
Are these the same plates that cause tsunamis or?
Earthquakes and yep. Okay, so
It's like tectonic plates or something?
yeah, plate tectonics, that's what it is. All the, all the changes that happen on the surface of the earth, earthquakes and stuff like that happen at plate boundaries and stuff. Okay? So it's the 1% thickness, okay? So oh man. All right, so here is a, oops. Here's a one plate going in underneath another plate. Okay, so this plate is going in underneath the other plate. These plates get stuck because they're constantly in motion, but they get stuck. And when the plates slip, that's when an earthquake happens. Okay, so when this happens, the ocean underneath here bounces up and down, and that's a tsunami. That creates a tsunami. Okay. So here's new plate being created. So there's the asthenosphere. Okay, so new plate is rising, new plate is created here. So Iceland straddles that, and these plates are moving away. Okay, so these plates are moving away. This is where plate is being created. This is where plate is being destroyed. These are called what is that? Transform boundaries. Okay, so that's what's happening in California. So these two plates are moving side like that, and they get stuck, and when they break loose, that's when earthquakes are created. Okay, so all right, so here are the plates. Okay, and at plate boundaries is where you harness geothermal energy. Again, only 16 Hoover Dams worth of geothermal energy is being harnessed worldwide. And you need 1,000 times more than that, 1,000 times greater than that to run the world. 16,000 gigawatts is what you need. All right, so you learned that, okay. You learned that to produce electricity, you need to get to a temperature of around 200 degrees Celsius, okay? And you have to go fairly deep. The question is how deep? About 4 miles, okay? Now, if you can get to 200 degrees faster, then it'll cost you less to produce electricity, okay? So you're looking for the best locations. Where do you get to that temperature fastest, okay? Or, stuff like that. So here's a picture that shows you this. Okay, this shows you, okay, so normal geothermal gradient is about 25 degrees Celsius per kilometer. What do you think that number means?
Like it raises 25 degrees,
Yeah, exactly. Every kilometer you go down, the temperature rises by 25 degrees Celsius. Okay? So if you want to get to 250 degrees Celsius, you have to go 10 kilometers. Okay? What is 10 kilometers? 10 kilometers is from here to Ormond Beach. Okay? You'd have to dig a hole that deep. Okay, so that's the new geothermal. Okay, we'll come to this. Okay, what is this guy? Okay, so rock is solid up to that point. Beyond that point, rock becomes becomes plastic. Okay, so that's the solid boundary. Okay, so, and it melts. So for instance, here in this pocket, okay, so okay, so there is the solidus boundary, here is the geotherm. So if the temperature goes past that point, you would get magma, molten rock. Okay, that's the stuff that comes out in volcanoes. Okay, there's magma. Okay, so if the geothermal, okay. In locations like this, the solid boundary is much shallower. Okay, and you can get magma. So here you have magma here. Okay, in hot spots, what are these are magma pockets underneath, and if you're digging close by there, you you get you cross the solidus boundary. Okay, and again here as well. So this is normal geothermal gradient is in normal locations. Okay, so that's what that diagram is showing you. All right, so again, what you are looking for is, so this is depth and this is temperature. You want this curve to be as steep as possible. The steeper this is, the more you like that, because you're getting to a higher temperature faster. That's what that says. Okay, so that's the kind of stuff you're looking for. Did you guys understand that? All right. All right, so we'll look at some, we'll look at various sources. Hot, dry rock, hot water reservoirs. What does this mean? You've gone to depth and you found hot rock, except that it's dry. Okay, what is it that you want? You want steam to turn your piece of wire. Okay, so this doesn't have water, so what are you going to do? Well, there's a bunch of hot rock there, so what you're going to do is you're going to, I'm sorry?
Pour water.
There, exactly. See, you could be a billionaire. Okay, just dig a hole, pour water there, it boils, bring up the steam, and you turn your turbine. Yeah.
What is the difference between the normal situation and a mid-ocean ridge on the little grass?
See, at the mid-ocean ridge here, near here, the temperature is rising very fast. You don't have to go too deep at all. It's rising very fast. And Iceland is somewhere there, so you don't have to go deep at all in Iceland to get to hot stuff. Yeah. Near plate boundaries, the gradient is much higher, as can be seen from the diagram. So this is near plate boundaries. The temperature gradient is much higher. The temperature is dropping very fast. I mean, is rising very fast. Yep. All right, so hot, dry rock is you've gone deep and you found a bunch of hot rock, except that it's dry. And so you got to pour water and bring up that heat. Hot water reservoirs, if you can find this is good. You find a pocket, whatever at depth, 2-3 kilometers deep. 2-3 kilometers is, let's say, from here to US 1. Okay, that deep, you find a hot water reservoir. You just pump up the hot water. Okay, and then produce electricity. There are natural steam reservoirs. Again, you're all looking at this. So here's this. This is about 2 kilometers, let's say, and you're looking at various reservoirs underground. Okay, if you find steam there, then you just pump up the steam and drive your turbine. Okay? And as you go deeper, there's pressure. So there are geopressurized regions where you can find hot water mixed with methane. What is methane? It's a greenhouse gas, but that's natural gas, but you can burn this. My generation doesn't worry about your generation or future generation. We're just going to get rich fast.
Did you say, isn't it cutting holes in our atmosphere or something?
I'm sorry?
The methane gas?
No, it's a greenhouse gas. It traps infrared radiation about 80 times stronger than CO2. So it's a very potent greenhouse gas. All right, but there are reservoirs where brine and methane is mixed. So you pump it up, you use the heat to produce electricity, and you can burn methane to produce electricity as well. Okay, so what we are looking at is all different kinds of sources. Again, most of these are about 2 to 3 kilometers down. We are looking at these reservoirs that contain one of these things, and we have the technology to harness the energy. Okay. Again, what kind of energy are we bringing up? Heat, mostly. Okay. Okay. All right, so here's hot, dry rock. Okay, so again, here's rock, and this is about 4 kilometers deep. So what you do is you pump down cold water. Okay, now hot, dry rock is extremely abundant source of geothermal energy. A vast source of thermal energy is contained within this hot, but essentially dry and impervious crystalline basement rock. It's dry, no water, impervious. Okay, so water won't leak if you let's say blast a hole in there, or what is called as fracking. You frack this rock. Again, there are techniques for doing this. You frack this rock, then pour water, and this water won't leak away, run away to Japan. Okay, and you pour water and then pump back up hot water. Okay, and once you have hot water, you know what to do with it. Okay. Okay, the source has been tested extensively with multiple deep wells drilled in several areas around the world. Except that right now, so why don't we use this? Because it's too expensive. Okay. It's easier to harness solar energy.
Why did they say fracking is bad?
Your house sits on a foundation. What if I crack the foundation?
It's not gonna be good for the house.
That's right. Okay. So we claim that fracking causes those mild tremors and stuff like that. Okay. All right. So again, right now this is too expensive. There's plenty of it there. Okay. But again, sunlight is falling on you, and we're just waiting for cheap batteries. Okay, and that'll happen. So again, to harness this, you want to get to hot temperatures as fast as possible. So in principle, with a gradient of up to 40 degrees Celsius per kilometer, a well can be drilled potentially economically. Okay. And what you do is you pour cold water, you frack this rock, and then pump up the hot water and produce electricity. So, but right now these are not commercially viable. Okay. You might have a hot water reservoir, okay, and then you just pump up the hot water and replenish it with cold water. Again, pump up the hot water, the steam, you extract the heat. The steam generated turns a turbine, which turns the wire. Again, the turbine goes into the generator and you produce electricity. So hot water may be extracted from these wells, which may either be used for space heating purposes or generating electricity. So if the steam is hot enough, then you produce electricity, and if it's not too hot, then you can use for space heating.
So on the way up, does it not cool down?
No, it doesn't.
If it is not too hot, then?
You use for heating up north, space heating. In the winter, you need to heat your house here. Not in Florida, but let's say you were in New York and stuff like that. People up north spend about $5,000 a year heating. Has anybody lived in the snow belt? Where?
I just kind of lived where it snows in
I'm sorry?
I just kind of lived where it snows in Pennsylvania.
Okay. So such resources are used widely in Iceland. That's because it gets hot very fast. You don't have to go that deep in Iceland to get hot. Again, what does the marketplace do? What does the marketplace do? It's always looking for the cheapest solution. Again, the idea is the following. I mean, if you have to feed 10,000 people, are you going to buy filet mignon? No, you're going to buy burgers. That's the idea. I mean, yeah. So. All right. So here's natural dry steam reservoirs. Dry steam means the steam is not mixed with water. Okay. So near volcanoes and stuff like that, you might have a geothermal reservoir. This could be just steam. This could be steam and water, whatever. Okay. And you pump this up. You turn your turbine, which turns that piece of wire in there, and you produce electricity. And you send the electricity to people's homes and charge them an arm and a leg. Yeah, and that's the idea. And then you have to pump the water back. Yeah. Why do you pump the water back? Because otherwise you'll run out of the source soon. Yeah, so the Geyser Reservoir in Northern California is currently the world's largest known dry steam resource. Typical facilities of this type have capacities of 50 megawatts of electricity. That's what that subscript is. Is this a lot? A large windmill will produce 15 megawatts. This is 3 windmills. You can put up 3 windmills in 6 months. Okay. So why do we have this? Well, I mean, it's $5 lying on the sidewalk. And that's all we're doing. Okay. All right, so here's a reservoir. This is hot water. See, this is molten rock that's heating this reservoir. Molten rock and steam, and you can pump up the steam, okay, and pump the water so you have a constant source of steam, all right, as long as possible. Okay. You guys understanding this? All right. All right. So geopressurized regions, these are regions where, what this is showing you is, okay, so bacteria will produce methane, and this methane can get, gas-rich brine, salty water mixed with methane can travel down, and it can collect in geopressurized regions, okay. Are hot brine aquifers containing dissolved methane trapped under high pressure in sedimentary formations at a depth of 4 to 5 kilometers. The energy potential includes both thermal energy in the hot water and the methane stored in the reservoirs. The thermal energy can be used in a steam-driven electric generator, and the methane can be used as fuel. Yeah. All right, so again, in all these things, here's so you have rock, which is 2 to 3 kilometers, 4 kilometers deep, which is how much? From here to, let's say, the US 1 or the beach. That's how deep you have to go. Okay. You get to a hot source. What you do is you might have to frack this rock. You pour cold water, bring up the hot water. The steam which turns a turbine, which turns that piece of wire between magnets, and you produce electricity. And then you have to replenish that with cold water. Okay. So this is production well, and this is injection well. Injection well is where you're putting back the cold water. You know. Okay, so again, there are 2 or 3 different technologies to produce electricity, depending on what it is that you're getting. Dry steam is you're getting pure steam up, and so this would be the cheapest. You just turn the turbine, which turns that piece of wire. Flash steam, okay, so what it is it's water under high pressure, and when you bring that water up, it becomes steam in a flash, right? And then you turn the turbine. and those are flash steam. Binary cycle power plants are where the water coming up is not super hot. And so what you do is, let's say you bring up the water and then you can vaporize, let's say, alcohol. What you need is vapors to turn this turbine. Okay, so if you have a source that is not too hot, you vaporize another fluid that has a lower boiling point like alcohol or something, and that turns the turbine. So you can't produce much electricity this way. Okay? Again, to put it in perspective, this is the world's largest plant, roughly, and you're barely producing 3-4 windmills worth of electricity. Okay? But again, you're doing this because it's cheap, and it's free. Okay? Okay, so these are the various kinds of power plants. The binary cycle is where the transfer heat from geothermal hot water to another liquid. So this is where the hot rock is not too hot. Okay, flash steam plants, that's the flash steam plant. Okay, some deposit contain hot pressurized water. When the hot pressurized water is pumped up to the surface, the lower pressure at the surface causes the water to vaporize instantly to steam. Okay. So that's what you're doing. This steam can be used to produce electricity. So the binary cycle, in binary cycle plants, the thermal energy of the hot water or steam is transferred to a second working fluid through a heat exchanger. So this is hot water coming up, there's the heat exchanger, there's the alcohol, if that's some organic compound that's flowing through, that vaporizes, and that vapor is turning the turbine. Okay. Again, you use this when you don't have too large, the stuff coming up is not too hot. This system has the advantage that a working fluid with a boiling point that is lower than that of water can be used, thus allowing geothermal reservoirs with lower temperatures to be used for electricity generation. Okay, so this is geothermal energy in the last 100 years. Okay, so initially the use grew, but now we've tapped up pretty much everything. And again, only about 16 Hoover dams worth of, in 2020, globally only 16 Hoover dams worth of geothermal energy was tapped. Okay, very little, peanuts. Okay, 1 cent to $10. This is a good application for geothermal energy, and this can be used in cold countries. Okay, so so let me show you. Here is a good map to remember and study this carefully. Not for exams, just for, at well depths of 30 to 60 feet. So dig 30 to 60 feet. Let's say 30 feet is the height of this building. So if you go that deep, okay, in Florida, the temperature is a constant 72 degrees. Okay. Here it's 42 degrees Fahrenheit. All right, let's say we are living there, 42 degree Fahrenheit. Okay. In the winter, what's the temperature in your house?
42.
No, that's the ground. In the winter, the temperature in your house is, let's say you don't heat it, it's about 20 degrees Fahrenheit. So what you do, you take that cold air. I'm just simplifying this. There's other technologies to do it. So in the winter, the temperature is 20 degrees. You send this cold air through there, it warms up to 42 degrees. Okay, you bring that warm air up. Okay, now 42 is still cold, so you warm it a little more using electricity. But you saved quite a bit of money warming it up from 20 to 42 for free. Okay. In the summer, it's hot, let's say 90 degrees, the air is 90 degrees. You send that hot air, it cools down to 42 degrees, you bring it up. Okay, that's the idea. Okay, so you have a steady temperature that's good in the winter. You take cold air, and again, but you do it in a better way. You use heat pumps and all that kind of stuff. What you do is you actually you use some kind of coolant some kind of fluid as a heat exchanger. Okay? But the idea is like I said, the simplified way. Okay, so there are houses in Florida where you don't have heating and cooling. You're using geothermal energy. Okay, so in Florida is perfect here. This is, you know,
Is there a reason that most houses don't have it?
well,
I mean, 72 is a good temperature in the summer and the winter.
I'm sorry.
Like,
Yeah.
is there a reason we don't use geothermal more here?
I don't know all the reasons. You hit water pretty soon in Florida. I mean, at least if you're close to the beach. It could also be that, so up front, maybe the house might cost $20,000 more, and it's like solar panels. Why there are solar panels on every house in Florida, you know? Okay. So there are geothermal systems can substantially reduce home heating and cooling costs. So what this is telling you, heating and air conditioning are 60% of your energy bills at home. Lighting and appliances 27%, and hot water is 13%. Okay. So if you have a geothermal system, half the energy come from geothermal energy. So your electricity bill is cut in half. Okay. And then you need to supplement that, 18% of your bill will be there. Okay. So, and up north, they do sell quite a bit of geothermal systems. So here is a geothermal system. So you lay these pipes before you build the houses. And here is a heat exchanger. Okay, so in the winter, you pump down cold fluid. This warms up, and you take that heat and warm the house. Okay. And in the summer, you do the opposite. You absorb heat from the warm air, send that warm fluid, which cools, and then use the cool air to cool your house. Cool fluid to cool your house. Okay. Okay, now we'll talk about direct use of geothermal energy. That is, we're going to use that heat and not produce electricity. So okay. A survey of 16 western states identified almost 12,000 thermal wells. Again, thermal wells are heat coming up or warm water coming up from the locations where the warm water is coming up. So there's some kind of heating mechanism for this water close by. Okay. So these are low to moderate temperatures, 20 to 150 degrees Celsius. So here's alligators being raised in Idaho for their skin and meat and stuff like that. In Idaho, right? Because this is.
Wait, they actually have that in Idaho?
Yeah,
Oh,
They eat it?
yeah.
you can eat alligator.
Like, they're not every day.
Well, I suppose you could use it for the pet industry.
Wait,
What? I don't know if they
use
use
it for
it.
the pet industry, like have the
Like
pet
a zoo?
alligator?
No. Use the alligator meat for the pet food. That's a multi-billion-dollar industry.
Don't forget the fancy boots.
And don't forget the fancy boots. Yeah. Well, the skin is yeah. The
Like the fancy boots.
the pet food is just an icing on the cake. The cake is the fancy boots. And alligator. Yeah, no, really. Alligator skin is.
Are they really make from alligator?
I'm just. I don't know. Maybe. Hey, they put worse stuff in pet food.
Do you think they let the Idahoans, or how, I don't know,
Mhm.
I would call them, but visit the alligators, since it's not like you're not before? Like, oh, come visit the alligators.
Like tourist attraction?
Yeah.
Like Niagara Falls.
Yeah. I know, they don't really have them wandering around
Yeah.
up there like we do down here.
Well, alligators unfortunately are not as pretty as Niagara Falls. Okay, so direct use of geothermal resources in the use of underground hot water to heat buildings, grow plants in greenhouses, dehydrate onions. I didn't know this was this onions and garlic, heat water for fish farming, pasteurized milk, and for many other applications. Okay. So if you have sources like that, you don't have to burn coal, you don't have to use other electricity and stuff like that. Okay. Again, wherever you can save money, you save money. Okay. Okay. So if you have a free source of energy there, instead of building a plant here, you'll build it there. You know. That's the idea. Okay. So here in in Iceland, you're pumping hot water from the geothermal source, putting these pipes underneath and then laying the sidewalk. So your sidewalk never freezes, and you don't slip and fall, and you don't break bones when you get old and stuff like that.
I've seen that in like fancy driveways, and that's really cool. It seems kind of expensive though.
You've seen this in Florida?
No.
No.
On TikTok in the fancy.
Oh, okay,
driveways,
okay,
when they're like,
Yeah, yeah.
"Oh, I have a heated driveway."
Right. So, shown in the picture is use of geothermal hot water to prevent icing on sidewalks in Iceland. Yeah. Again, why don't we do this in New York?
It's only $5.
I'm sorry? Yeah, this is expensive. I mean, when do you do this? When you have free hot water. And when you don't have free hot water, you don't do this. Okay?
It could be like life-saving though, because then we had like a really bad snowstorm like last year, I thought, and there were a lot of crashes and people getting stuck on the road, and they couldn't find the road, so then people were driving into like the rivers or whatever.
This would be useful for roads though, because of road maintenance.
Oh, okay.
It's too expensive. Okay, so I live in this. Well, I'll tell you as soon as we stop recording. Okay. so, so advantages and disadvantages. Geothermal energy. High energy density per land area when available. It's a simple and well-established technology. Okay. And it's relatively safe with minimal environmental impact. So you'll harness it when you can. Okay, so reinjection of water may lead to geological instability, and as in the case of fracking, those are the tremors that cause. Okay. So again, this is a source with relatively low environmental impact. But again, this cannot solve world problems. It's only 1 cent to every $10. Okay, 0.1 to 1% of the world energy source. But I mean, if it's easily available, then we are going to harness it, and Iceland does that.